From the sun, a constant stream of radiant energy pours down through the atmosphere. At the Earth's surface, this radiant energy is converted into heat energy. This heat energy melts snow. And it evaporates water. It forms clouds and drives the winds. It can reappear as electrical energy and sound energy. Solar radiation is absorbed by vegetation, which converts it to chemical energy. Each year, we watch the ever-repeated cycle of plant growth. The human race, indeed the rest of life on Earth, depends on the energy stored by plants for its very existence. How does this radiant energy produce so many effects? To answer this question, we must learn more about its nature. When light from the sun passes through raindrops, it is separated into the many colors of the rainbow. Similarly, when light from a lamp is passed through a slit, a lens, and then a prism, the spectrum produced shows the colors present in the light. When this red liquid is placed in the path of the light, the blue and green colors in the spectrum are removed. This part of the light has been selectively absorbed by the liquid. The blue and green light absorbed by the liquid is converted into heat. The movements starting to appear are convection currents caused by heating. If we could see the individual molecules in the liquid, we would find that they move more quickly as the light is absorbed and the temperature rises. Selective absorption, very similar to that which we have just observed, also occurs in the atmosphere. And in this film, we will explore some of its effects, since they influence not only the entire atmosphere, but also the surface of the Earth and the life which exists here. We begin our story with the white light spectrum. Note how one color merges imperceptibly into the next. At each end, red and violet fade gradually into black. Although the screen appears dark, this does not mean there is no energy arriving. On the contrary, there are considerable amounts of energy, both beyond the violet in the ultraviolet and beyond the red in the infrared regions of the spectrum. In a classic experiment carried out by Sir William Herschel over 150 years ago, thermometers were placed in the spectrum of sunlight. The temperature readings traced out a smooth curve across the spectrum. These readings are a measure of the radiant energy in different parts of the spectrum. Notice there is energy in both the ultraviolet and the infrared. How does this radiant energy travel from the sun to the Earth? In one description, the energy is carried by small particles called photons. Let us consider light of a single color produced by identical photons. As the number of photons increases, the light becomes brighter. These photons can pass through transparent substances such as glass. They can be scattered, or they can be absorbed. When they are absorbed, the photons disappear, but their energy is given to the absorber. We can describe the radiation in different parts of the spectrum by the energy carried by single photons, since photons of the same color all carry the same energy. For example, photons of violet light have about twice the energy of photons of red light. Ultraviolet photons are much more energetic than infrared photons. Each photon has a characteristic wavelength associated with it. These wavelengths are very short, and a special unit, a micron, 1/1,000,000th of a meter, is used to measure them. Red light has a wavelength of about 0.7 microns, and violet light a wavelength of about 0.4 microns. The very energetic ultraviolet photons have much shorter wavelengths than the less energetic infrared photons. Today we can repeat Herschel's experiment and measure the amount of solar radiation at each wavelength. This curve, measured at the bottom of the atmosphere, extends into both the ultraviolet and the infrared. Might it be possible that in space the spectrum would extend even further? Today we can measure solar radiation far above the ground with instruments carried by balloons, rockets, and satellites. The measurements have shown that the solar spectrum outside the atmosphere does extend to much shorter and longer wavelengths. However, 99% of the energy lies between 15/100ths and 3.5 microns. About 15% is in the ultraviolet, 35% is in the visible, and 49% is in the infrared. Part of the ultraviolet and infrared radiation from the sun is selectively absorbed as it passes through certain regions of the atmosphere. What causes this absorption? Why does it occur in certain levels and regions? To understand the nature of this absorption, we must first understand the composition of our atmosphere. Almost 4/5 of our atmosphere is nitrogen. 1/5 is oxygen. In addition, there are small amounts of water vapor and other gases, some of great importance, such as ozone and carbon dioxide. If we could look closely, we would see the air molecules traveling quickly in all directions and getting fewer as we go higher in the atmosphere. When energy is added, the average speed of the molecules increases and the temperature of the air rises. One way of adding energy is by the absorption of photons. Even if only one of the gases in the atmosphere absorbs photons, the energy added will be shared with the other gases because of the collisions which are continually occurring, and this raises the temperature of the entire region. Oxygen in the high atmosphere absorbs many of the incoming ultraviolet photons from the sun. In fact, radiation at wavelengths shorter than 0.15 microns does not penetrate below about 80 kilometers. When these photons are absorbed, they not only make the molecules move more quickly, but some have sufficient energy to separate, dissociate oxygen molecules into 2 oxygen atoms. Other ultraviolet photons can detach an electron from the oxygen molecule and leave it ionized. Thus, the nature of the high atmosphere through which Earth-orbiting satellites travel is very different from that near the surface. Because there are free electrons and ions present, this region can readily conduct electricity. And there are so few atoms and molecules that it behaves as if it were a very good vacuum. But the atoms and molecules present travel so quickly that the temperature is high. Lower down, near 50 kilometers, the atmosphere is heated by ultraviolet photons of longer wavelength. These less energetic ultraviolet photons are absorbed by ozone. Ozone is formed by the combination of oxygen molecules and free oxygen atoms. To discover what determines the temperature of the lower atmosphere, where airplanes travel and where temperatures are often measured by balloon-borne radiosondes, we must find out what happens to the rest of the solar radiation. On a clear day, 80% of the incident solar radiation reaches the Earth's surface primarily in the form of visible and infrared radiation. Even on a cloudy day, 50% can reach the surface after being scattered by clouds. A small part of the radiation is used by plants, but most of it is converted to heat energy. Some of this heat energy evaporates water and melts snow. The larger portion, however, heats the surface. The air molecules collide with the surface and are heated. The air becomes more buoyant, and it is pushed up by cooler, less buoyant air, which in turn is heated. In this manner, heat energy is added to the lower atmosphere, and convection currents are formed. The warm rising air carries molecules of water vapor. As it rises, the air expands and cools. Eventually, the water vapor condenses to form clouds. The cloud-filled air rises until it cools to the same temperature as the air around it. Thus, surface heating by solar radiation causes rising air over warm surfaces and descending air over cool surfaces. The resulting winds carry energy from the warmer to the cooler parts of the world and from the surface to as high as 12 kilometers. This part of the atmosphere is called the troposphere. So far, we have seen how the atmosphere gains energy. There must be some way for the Earth-atmosphere system to lose energy. Otherwise, it would continue to become hotter and hotter. The system loses energy by itself radiating to space. All bodies radiate. The amount and nature of the emitted radiation depends on both their temperature and their composition. The hot sun emits large amounts of ultraviolet, visible, and infrared radiation per unit area. Objects near room temperature emit much less radiation per unit area, and this all lies in the infrared. Most of the solar radiation lies near the visible part of the spectrum. But the terrestrial radiation lies at much longer wavelengths. If we consider the total amount of solar radiation which falls upon the Earth and the total amount of terrestrial radiation emitted in all directions out to space, we know that on the average these must be the same, since the Earth's temperature does not change from year to year. Thus, the two curves are drawn the same size. Part of the solar energy absorbed by the sunlit surface of the Earth is lost by infrared re-radiation. This is in addition to that lost by convection. At night, the Earth's surface continues to radiate. Since no solar radiation is received, the surface cools and convection is greatly reduced. Some of the infrared photons emitted by the Earth's surface pass directly into space. Others are selectively absorbed by the atmosphere. These photons are an additional source of energy to the atmosphere. However, the gas molecules which selectively absorb also selectively emit infrared photons. In this way, the atmosphere loses energy. This exchange of energy between photons and molecules is complex. But since it influences the temperature of most of the lower atmosphere and also the Earth's surface itself, we must look in more detail at some of the processes which can occur. The important molecules which absorb infrared photons are water vapor, ozone, and carbon dioxide. An infrared photon is absorbed by a carbon dioxide molecule, and its energy is increased. The energy is shared with infrared inactive molecules such as oxygen or nitrogen. Eventually, another infrared active molecule gains energy which is lost as a photon is emitted. Although many different types of interaction are occurring, we nevertheless find that when infrared photons fall on an air sample, the rate of absorption is not very dependent on the air temperature. But the number of photons emitted depends very strongly on the air temperature and decreases very rapidly as the air cools. Thus, if a sample of air is receiving energy only from incoming photons, it will absorb them at a constant rate, causing a steady increase in temperature. The number of photons emitted will depend on the temperature of the air sample. An equilibrium temperature is reached when the rate of emission of energy is equal to the rate of absorption. In this condition, the air is in radiative equilibrium. Now we can describe the temperature structure of the atmosphere. In the troposphere, the transfer of heat from the surface by convection is much more rapid than the transfer of heat by radiation. The average temperature decreases with height up to about 12 kilometers. Above the troposphere, temperatures are primarily determined by radiative processes. From 12 to 80 kilometers, infrared photons from the Earth and lower atmosphere are absorbed, and the entire region loses heat by radiating. The absorption of solar ultraviolet radiation by ozone near 50 kilometers adds additional energy. The air temperature rises so that this energy can be removed by infrared radiation. Above 80 kilometers, the atmosphere is also heated by the absorption of solar ultraviolet radiation. Since there are no molecules to emit infrared photons, the temperature is high, over 1,000 degrees Kelvin, above 150 kilometers. Returning from the high, thin, hot atmosphere to the surface, we find that the temperatures there are determined not only by the amounts of radiation being received and emitted, but also by the composition and density of the atmosphere which is present. After dawn, the surface is heated by the sun, but the temperature increase is often moderated by convection currents which carry large amounts of energy from the surface. On the moon, there is no atmosphere, and there are no convection currents to carry energy from the surface. Thus, daytime temperatures are very high. At night, the lunar surface radiates and cools rapidly to very low temperatures. The Earth's surface also cools at night. However, the atmosphere returns some of the energy it received during the daytime, and thus surface cooling does not progress as rapidly as on the moon. Nighttime temperatures are much lower when the air is calm and dry and there are no clouds. The atmosphere returns most energy to the surface when it is cloudy and windy. Because of the presence of the atmosphere and because much of the Earth is covered by clouds, it is estimated that the average surface temperature is 30 degrees Kelvin warmer than the average lunar surface. Besides moderating the temperature extremes we would otherwise experience at the surface, the atmosphere also protects living things from harmful short-wavelength radiation from the sun. Looking down on the Earth, we see by its appearance where clouds and oceans occur. Similarly, by observing the outgoing radiation from the Earth in the ultraviolet and infrared, it is possible to estimate the temperature of the atmosphere, the heights of clouds, and the amounts of infrared active gases present. Today, satellites circle the Earth carrying instruments for making these measurements, which will eventually give us better weather forecasts and perhaps show us how to harness the weather for all mankind.